And here it is. Okay. I'm going to step away and refill my coffee cup. I'll be right back. Welcome, Jose. Good to see you here this morning. Wei, Purdue.
See you, Paul.
Yeah, well,
Looking
you're the
forward
one
to
that
the
introduced me to
presentations.
Joanna, so you should be here.
Yes.
You can help me with the questions and answers if you're interested in sticking around.
Oh, well.
Mhm. We'll start in about 30 seconds. Good morning and welcome to our technical meeting this morning. We try to get a technical meeting every month here in the Santa Clara Valley and San Francisco and Oakland East Bay sections Electronics Packaging Society chapter. We welcome you this morning. We have a number of volunteers that work on these with us. If you'd like to join us, um, you can email any of us, and the emails are shown here in the lower quadrant. We have an active program committee that meets, and you can join us and help us select future topics and help us when we have a in-person meeting. Usually we hold them at SEMI headquarters in Milpitas. We have a slate of upcoming talks. We have today's talk, of course, on April 25th on chemical mechanical polishing, which is used for thinning and polishing wafers for hybrid bonding. So we have a gentleman from Applied Materials that will be speaking. In May, the first week of May, we have a build-up substrate symposium. This is an issue. We can obviously fund lots of um, semiconductor companies, but if they have to ship all of their products from the USA to Asia to be packaged, that's not exactly the solution we're looking for. So we're going to be talking about substrates and the infrastructure in North America for that. And that will be a large, you'll be hearing more about that in the future. In June, a talk on 2.5D silicon photonics interposers for flip chip attach. That should be of interest also to a number of our people. We have a pretty active chapter. We invite you to join us. You can go to our website here. And I also point out that most of our talks are on IEEE TV. You can also get them at the EPS Resource Center. So just to let you know that if you miss a talk, or you are in the wrong time zone for our talk, usually it'll be edited and placed on our website, a link on our website to IEEE TV or to our resource center. So introducing our first speaker today, Joana Mendes is going to be talking on using diamond films to enhance thermal performance in electronics packaging. We've been hearing about this possibility for years. They're using some of it, but it's been very expensive and difficult to access. Joana graduated from the University of Aveiro in Portugal in electronics and telecommunication engineering in 1998 and got her PhD in 2006. She's now a researcher at the Institute for Telecommunications in Portugal, working toward integrated artificial diamond and power electronic devices specifically. So we'll be hearing from Joanna first. Our second speaker is Dr. Jeroen van Duren. He got his degree from the University of Technology Eindhoven in Netherlands, a PhD in chemical engineering and chemistry in 2004. And he's the VP of Technical Applications at Diamond Foundry in South San Francisco. He's worked in various industries, the semiconductor industry, photovoltaics, display technology, metallurgy. He's published over 40 papers and filed many patents. So we welcome Jeroen this morning for the second half of our talks. So with that, I'm going to pass control to our first speaker, Joanna.
Okay, I'm trying.
Just a moment.
Share. Okay.
Now you should have the share button.
Now, yes.
Okay.
So just share, and now we should go. Okay, straight to my talk. Okay.
Full
So
screen.
can you see it?
It looks good and you sound fine.
Oh,
Thank you.
okay. So thank you, Paul, for the introduction. Like Paul mentioned, I'm a researcher at the Telecomunications Institute, and I've been working with diamond films for more than 20 years now. And I'm going to try to convince you how we can use diamond to enhance the thermal performance in electronics packaging.
Joanne,
short-
if you can hide that notice at the bottom, that way we will
Oh,
see it. Hit the hide.
okay, hide.
There you
Okay,
go.
hiding.
Go ahead.
Okay, just one thing. Pointer laser in case I need. Okay, so a brief outline. I'll really go very quickly through the motivation because I don't need to tell you why we need to worry about thermal management. And then, yes, I'll try to convince you why should we consider diamond. I will briefly mention how we can fabricate artificial diamond, and then I'm going directly to the results that have been obtained so far with respect to the use of diamond for thermal management of power components, namely gallium nitride HEMTs, the use of diamond as a chip carrier inside power packages, the use of diamond as a power board, and then I will draw my final conclusions. So just to give a brief overview, I decided to think about a data center because we can think of thermal management at all levels. So from the room level with air conditioning, then we can go to a system or a computer, so to speak, where we can have, for instance, liquid cooling like gaming computers. We can think at board level for some specific components like power LEDs, where we can use power boards, or we can also have convection or radiation cooling or thermoelectric coolers in specific places. Of course, you can have heat sinks, and we have power packages. And inside the package, manufacturers can choose chip carrier, die attach, and thermal interface materials with high thermal conductivity, and also implement thermal vias. And finally, in some cases, we can even think about chip level because we can choose a proper substrate material with high thermal conductivity. And actually, diamond can be fitted here at the chip level, package, and also board level. And now, why diamond? Well, diamond is one of the carbon allotropes, and the carbon atoms are arranged in the face-centered cubic crystal structure that we know as diamond lattice, meaning that you have a central carbon atom surrounded by four adjacent neighboring atoms. And if you look at the periodic table, carbon is here. It's a very, very small atom. And this gives rise to an extremely strong covalent bonding between the sp3 hybrid orbitals because these atoms are really close together. So their distance is only 0.15 nanometers in the diamond lattice. And this is what, in the origin of diamond's extreme properties, such as high hardness. So diamond is the hardest material known to man. High chemical inertness, so you cannot etch diamond with any liquid whatsoever. It has a very high ion modulus, so it's a very rigid material and has a correspondingly high surface acoustic wave velocity. It has a high thermal conductivity, 5 times higher than copper. And it also has a high band gap and high breakdown field, so 5.47 EVs for band gap and 10 megavolt per centimeter breakdown field. So this makes diamond an extremely good electrical insulator. It has a high electromobility and it has a low dielectric constant, 5.5. In addition, it's radiation hard. It has a low thermal expansion coefficient, about 1 ppm per Kelvin. It's optically transparent, has a low refractive index of 2.38, and has a negative Bohr function and is biocompatible. So it has a series of properties. Many of them are relevant for our particular application. And now, how can we fabricate diamond? Well, natural diamond is formed deep in the earth mantle under extreme conditions. And then when there's a volcanic eruption, the magma will bring the diamond crystals close to the Earth's surface, where it is then mined. And despite having a high commercial value in jewelry, it cannot be used for electronic applications because natural diamond crystals have too many defects. So they are mainly limited to tribological applications, in addition to jewels, of course. And now, to fabricate artificial diamond, we can use the high pressure, high temperature method, where we basically try to reproduce the same conditions that are required inside the earth mantle. So we place the diamond seeds inside or at the bottom of a press at a high pressure of 5 gigapascal, and then we heat the press above 1400 degrees C, and this melts the catalyst, which is a solvent metal here. And when this metal melts, it will dissolve and drag atoms from the graphite carbon source all the way down to the seed crystal where they will precipitate. And in the end, we have nice crystals, which then can be cut and polished. And you can see that they come basically in two colors. So you have the transparent one, without color, and you have the yellow diamond, simply meaning that it's rich, it is nitrogen rich. And then these crystals are very, very perfect. They have high thermal conductivity, up to 2200 watt per meter Kelvin, and they are optically transparent, but their size is limited to 10 times 10 to the millimeter square, typically. But then we can also fabricate diamond by chemical vapor deposition. And here you can see the phase diagram of carbon. This will tell us, depending on the temperature and on the pressure, type of carbon allotrope will be formed. So graphite, liquid carbon, diamond here at the HPHT regime. And you can see that we have here the metastable CVD diamond phase below atmospheric pressure and at moderate temperatures, where we can also fabricate diamond. And how can we do it? Well, to begin with, the carbon is supplied as a gas. So typically we have methane molecules together with hydrogen. And then we have an energy source which will dissociate the molecules. So we'll have atomic hydrogen and carbon active radicals. And then these radicals will flow and react with the carbon atoms present on a substrate, and then a diamond film will start to grow. And then we have atomic hydrogen in excess, and this atomic hydrogen will etch away the non-sp3 bonds. So in the end, we'll have a closed film, mostly diamond, that is covering a substrate. And depending on the energy source, we can use hot filament, we can use microwave power and supply it through a waveguide, or we can also use microwave power, but use an array of linear antennas. For instance, hot filament, it's a very simple system. Here you just see a filament, which can be straight filament or a coiled filament. It's very simple. It's a low-cost system. It can be easily scaled up because we just add more filaments in parallel, for instance. We can use it to coat complex 3D substrates and internal surfaces by arranging the filaments properly. However, the filaments melt, so typically they are used at a maximum temperature of 2200 degrees C. But then we have a low production of atomic hydrogen and carbon radicals, meaning that we have low deposition rates, we have contamination with atoms from the filament, and last but not least, we have an extremely high energy consumption. So typically these systems are only used for tribological applications. But then we can also have supply the energy as a microwave being generated here in a magnetron, and then the waves are travel through the waveguide into the chamber, and they create a plasma ball. Well, it happens that this plasma has a very high density with high energy electrons. So we have a high concentration of atomic hydrogen and carbon radicals, we have higher growth rates, and we can prevent the contamination with foreign atoms. However, the deposition area is limited by geometrical factors. So we are typically limited to 4-inch if we use 2.45 gigahertz, or to 6-inch if we use 915 megahertz, even though these systems are a bit tricky. But we can also supply the microwave energy as TEM or TM waves. And in this case, instead of having a waveguide, we can have a coaxial line. And we supply the microwave power through the coaxial line. And then inside our system, we will have dielectric tube, we can think of it as a plasma line, where the external conductor of the coaxial line is actually replaced by the plasma. So we have the plasma line, you see here the electric tube, and plasma glowing all around the tube. Here you see the schematic of such a plasma line with a coaxial input from both ends. And the beauty of this thing is that we can have many plasma lines in parallel, as many as we want theoretically. So we can increase the deposition area up to 600 times 1000 millimeters square. So we can fit many wafers inside such a system. We have a high uniformity all over the deposition area, and we have a lower energy consumption with respect to hot filament CVD. However, and here you see two coated silicon wafers, 4-inch wafer and a 6-inch wafer. And however, these systems typically operate at lower pressures, so we have lower deposition temperatures and lower growth rates. And we also have smaller grain sizes, so this means that we have a lower thermal conductivity. And one more thing that I'd like to say is that we can either use a single crystal diamond substrate, and then we have homoepitaxial diamond films. So typically we use a hot HT HP crystal, and this is what we get out of the CVD deposition. After polishing, we get these nice transparent diamond substrates, which have the highest thermal conductivity of 2400 watt per meter Kelvin. And these are really ideal for electronic devices and thermal management. However, they are very expensive, and the limit is to a low area, up to 10 times 10 millimeters square. And then after my talk, Jeroen will tell you that no, we can grow them actually much larger, but I will let him explain that. We can also use an undiamond substrate. And in this case, we grow heteroepitaxial or polycrystalline diamond films. And see here, you see after polishing, we have transparent diamond wafers. These are 4-inch in size. We can grow them on different materials. And again, large area deposition is possible from 4-inch up to 600 times 1000 millimeters square. But since their nature is polycrystalline, they have lots of defects. So the thermal conductivity, when we have the regular microwave plasma CVD in a 4-inch diamond wafer, typically for 100 micron thickness, thermal conductivity is around 1800 watts per meter Kelvin. And if we go to the very thin films deposited by the linear antenna system, typical values for a 1 micron thick film are in the range of 80 to 500 watt per meter Kelvin, but these values can be further optimized with optimizing deposition conditions. And now that we know everything there is to know about diamond, how can we make diamond? Let's see how we can use it really to enhance the thermal performance in packages. So I'll start by talking about gallium nitride HEMT. And these devices, these are field effect transistors. The GaN layers are grown on a foreign substrate like sapphire, silicon, or silicon carbide. And they have here a barrier layer composed of aluminum gallium nitride. And here at the interface, we form the channel because we have a 2D electron gas with very, very high mobilities. So these devices are typically used for high power and high frequency operation. However, we'll have device self-heating. And since gallium nitride has a relatively low thermal conductivity, at least compared with silicon carbide, we get the generation or the appearance of localized hotspots. And this is really serious because in some cases, the amount of heat generated is comparable to the one we find at nuclear reactions and nuclear reactors, and at the surface of the sun. So you really see that we have to cool these hotspots down. And how can we do it with diamond? Well, we can simply cap the devices with diamond by growing diamond on top of the chips. And here the heat will flow through the AlGaN layer to the diamond heat spreader on top. Or we can also replace the substrate with diamond. And we can do it two ways. We can either grow the diamond on the back of the gallium nitride wafer, or we can just bond the diamond and gallium nitride wafers. And to start with the capping diamond, you see here the photo of a HEMT, GaN on silicon carbide HEMT, coated with diamond by Fujitsu. They deposited diamond films at 700 degrees C, and they used heat spreaders to transfer the heat from the top of the device where it is generated all the way down to the underlying HEMT holder. And thereby they reduce the thermal resistance of the GaN HEMT by 40%. And they also lower the junction temperature by 100 degrees at 25 watt per millimeter power. They had to do a small trick though. They could not use the standard Schottky gate contacts because they were damaged during the deposition of diamond. So they had to use MIS structure as the gate contact. A group in Stanford University, they used a different approach. So they used N-polar GaN HEMTs. And in this case, you see that the AlGaN layer or the AlGaN barrier is below the GaN cap. So the channel is formed above the AlGaN cap. And this is good because we can just extract the heat directly towards the surface without having to transport it through this AlGaN layer, which has a lower thermal conductivity. And these researchers used two different approaches. In the first case, they did what Fujitsu did. They deposited micron thick films, in this case, 2.2 micron thick diamond film on top of the structure. And on the other case, they coated the whole mesostructure with a thin layer, 500 nanometer, of diamond all around the device. So they created a short circuit, a thermal short circuit, so to speak, that allows the heat to flow from the top of the device all the way down to the semi-isolating silicon carbide substrate. And they got very interesting results. So for 25 watt per millimeter DC power, they managed to decrease the average channel temperature by around 80 degrees using both 2.2 micron thick diamond here or the 500 nanometer thick all around diamond. And in the later case, they reduced the peak temperature nearly 100 degrees C, plus or minus 20, at 9.5 watt per millimeter DC power with respect to the control device. And on top of that, they also verified that the cutoff frequency and the maximum frequency didn't show any significant degradation when compared to the passivation with the benzocyclobutene, a standard passivating material. With respect to diamond substrates, we can grow them on the back of the GaN wafer. So here we begin with the GaN wafer, typically GaN on silicon wafer. Then we just attach a temporary carrier on top of the GaN wafer. We flip the wafer over and we remove the substrate. And then we deposit a thin dielectric layer for protection of the gallium nitride layer. And then we just grow the diamond directly by CVD. And then we remove the temporary carrier and we are left with the GaN on diamond wafer. And here you see the first technology demonstration that was shown in 2006, where researchers from Group 4 Labs grew 25 microns of diamond on a gallium nitride wafer using a 25 microns, 50 nanometer dielectric layer. But curiously, this structure didn't show any thermal benefit. Actually, it behaved even worse than, for instance, GaN on silicon carbide. And why is so? Because the hotspots are here on top of the channel. But then between the channel and the diamond, we have all the aluminum nitride nucleation layers, we have all the strain relief layers and transition layers, and we also have the GaN buffer. And because this is required because we grow GaN on a 4-inch substrate, so we have to match the lattice mismatch, the lattice parameters. So we have a very large thermal resistance from the hotspot to the back of the diamond substrate. So what they've done, they've removed not only the silicon substrate, but also all these buffer and transition layers and also part of the channel. And they were left with 400 nanometer thick gallium nitride channel. That's where they grew the diamond. And with this structure, they obtained what is now currently the sort of figure of merit of GaN on diamond. And they obtained a 40 to 45% reduction of the junction temperature. And they managed to triple the aerial RF power density with respect to GaN on silicon carbide in 2014. And now In 2021, Akash Systems reported having achieved wafer volume manufacturing of 4-inch GaN-on-diamond wafers. They managed to obtain a uniform carrier bond in all the wafers of hundreds. It was about 100 wafers. They also obtained the limited electrically active traps at the GaN-diamond interface. Actually, as you move away from the channel, you see that the carrier density decreases. And here on silicon, you see the effect of traps, but in diamond, we only see the effect of traps after 10 nanometers into the channel. So this behaves even better than GaN on silicon. They got a uniformly low thermal boundary resistance at the interface all over the wafer. And they didn't see any degradation of the electron gas after the carrier wafer removal. And currently, they are supplying radios and power amplifier modules for satellite applications. So it's already achieved commercial application. We can also replace the substrate by bonding gallium nitride and diamond wafers. And we start with the same procedure. We have the GaN on diamond, the GaN on substrate, GaN on silicon substrate, for instance. Again, we attach a temporary carrier, and again, we remove the substrate. And then we just take a diamond crystal, whether single crystal diamond or polycrystalline diamond, and we may deposit an adhesive layer on both wafers, and then we just bond them together. And we can do it through thermocompression at moderate temperatures between 150 to 100 degrees C. We can use surface activated bonding at room temperature or van der Waals bonding at 300 degrees C. And of course, in the end, we just remove the temporary carrier, and again, we have GaN on diamond wafer. And here you see one of the first published results where the gallium nitride wafer was bonded to a 1-inch PCD diamond wafer, allowing for an increase, a 3.5 aerial power increase with respect to GaN on silicon carbide. And here you see a 3-inch GaN on diamond wafer with a functional device yield over 80%. And here in the right, you can see that the self-heating was actually reduced, because in gallium nitride HEMT, self-heating manifests as a decrease in the drain current for increased VDS values. So we can see that GaN on diamond indeed shows less self-heating than GaN on silicon carbide. To use the surface activated bonding, we start with both surfaces and we bombard them with argon ions. And this bombardment will create dangling bonds on both surfaces. And then when the surfaces are pressed together at room temperature in high vacuum conditions, these dangling bonds will convert into covalent bonds. And we can even use a few nanometer thick silicon interlayer to improve the adhesion if required. And using this method, Mitsubishi Electric in 2019 announced the transfer of a GaN on silicon multi-cell HEMT to single crystal diamond substrate using a 4 nanometer thick interfacial layer that you can see here. And you can see how the self-heating of the GaN on silicon was really reduced or even eliminated with the GaN on diamond HEMT. And 1 year later, Fujitsu also reported having bonded GaN on silicon carbide HEMT to single crystalline diamond substrates, thereby reducing the thermal resistance 1/3 to compare to that without diamond. And finally, the last process that we can use is the van der Waals bonding that was initially employed for gallium arsenide thin films. This process takes advantage of liquid capillary forces that attract the two surfaces, and it takes place at temperatures below 300 degrees C using a liquid like ethyl glycol or ammonium sulfide. You see here the flow of a particular process, GaN on silicon, attached to a temporary carrier after removal of the silicon substrate, and then the two to be bonded surfaces, the GaN and the diamond, and then the whole set mounted on a copper block. And here you see the IV characteristics of GaN Schottky diodes. First, the DC power increases as we move from silicon substrate to polycrystalline substrate to a single crystalline substrate. However, the researchers also reported that bonding to polycrystalline diamond substrates, so large area bonding, was not reproducible. And now we can also use diamond as chip carrier. And actually this work was carried out in my group, because we wanted somehow to provide the engineers with a figure of merit. So what can we expect if we take a power package and we replace the chip carrier with diamond? What will the impact on the device characteristics be? And so we chose as a proof of concept these 3 white lamp XPD LEDs. They have a very small footprint, 2.45 times 2.45, and they have an aluminum nitride carrier. And the thermal conductivity is somewhere between 60 to 193 watt per meter Kelvin, okay, because these are the values reported in the literature. And we evaluated what would happen if we replace this aluminum nitride carrier with single crystal diamond with high thermal conductivity, and also with polycrystalline diamond with 1800 watt per meter Kelvin thermal conductivity. And we used ANSYS to perform the multi-physics simulations. Of course, we had to make some assumptions. And we obtained these values for junction temperature as a function of the current. So the nominal current for these devices is 350 milliamps. So it will be here. And here you have the extreme results. So on the top, we can see the distribution, the temperature distribution for the diamond carrier, single crystalline. And here at the bottom, you have the temperature distribution using the worst aluminum nitride carrier. And here on the left, we have a nominal current of 350 milliamps. Here at the right, we have 800 milliamps. And curiously, in these two extreme scenarios, the junction temperature using a diamond carrier at 800 milliamps is 41 degrees, which is lower than the junction temperature at 350 milliamps using an aluminum nitride carrier. And we can also see here, especially from here, that actually it doesn't make that much of a difference to use single crystal or polycrystalline diamond in this scenario. So we proceeded to evaluate the impact of the diamond carriers on the luminous flux. So we took a look at the datasheet of the devices, and we calculated for the different types of LEDs, blue, green, amber, and red, what would happen to the relative luminous flux, and we saw that there's really not much difference. So replacing ALN with diamond doesn't bring any advantage in terms of luminous flux. And then we evaluated the stability of the wavelength with the current level. And here we calculated first, we estimated the band gap as a function of temperature, again, taking these parameters alpha and beta from literature. And then from here, we estimated the wavelength. And we've done this for three blue, green, and red LEDs. And we observed that if we compare the best case aluminum nitride, which is this one, with diamond, if we had a red LED, we managed to decrease the coefficient of variation of the wavelength with the current from a bit more than 0.7 to approximately 0.2 for the red LEDs. And for the blue LEDs, this coefficient decreased from 0.4 to a bit more than 0.1. So we managed to stabilize the wavelength with the diamond carrier. And this can be quite important in applications where the wavelength stability is critical, for instance, for visible light communications, or even in some space applications. And finally, we tried to evaluate the impact on the lifetime. So we calculated the time to failure using standard expression. And then we calculated the sort of acceleration or deacceleration factor of replacing the aluminum nitride with the diamond carrier. And we used the two extreme values of activation energy of the aging processes found in the literature. And if we consider that we have the best aluminum nitride, so we will have here the acceleration factor will be 1, and it will be lower than 1 when we replace it with diamond, because we are actually increasing the lifetime. And so, depending on the activation energy, whether it is 1.05 or 2.5, we could see that we can estimate that diamond will slow the aging of the LEDs by between 10% and 25% for nominal current. And if they are operated at 800 milliamps, the lifetime increase is between 30% and 50%. Of course, these values are even higher if we have the 60 watt per meter Kelvin aluminum nitride carrier, where the aging is slowed by between 35 and 60% at 350 milliamps, and between 60 and 90% for 800 milliamps current level. However, we should take into account that the simulations consider a perfect thermal contact between the chip and the diamond carrier. Because if this doesn't happen, if we have a high thermal resistance at the interface, actually we cannot extract the heat from the die down to the diamond carrier. And after having seen these results, we decided to experimentally test the use of diamond as a power board. So we used the same LEDs, and we simply bought metal core printed circuit board as advised by the manufacturer, and we bought a diamond board. So here I have the characteristics of the board. So this is a standard MCPCB board with copper metallization, dielectric insulator, and an aluminum core. And the diamond board that we bought, we had a 300 micron thick diamond plate with 1800 watt per meter Kelvin thermal conductivity, with a titanium tungsten gold metallization provided by the manufacturer. However, we had a really hard time when we tried to solder the LED to the diamond board. So we tried to use a lead-free solder, the one that we use to mount the LED on the metal core printed circuit board, but we simply could not bond or solder the LED to the diamond board, probably because this thermal conductivity is so high that the heating cycles, they were not adequate. So we'd really have to optimize the soldering process. However, after a couple of trials, we saw that the gold metallization had been taken away. We only had titanium and tungsten with a very high track resistance. So we decided to use silver conductive adhesive paint by RS Pro. And this will actually create a some uncertainty, because you can see that the thermal resistance between the LED tracks and the MCPCB will be much higher than the thermal resistance between the LED tracks and the diamond board. But still, we proceeded to evaluate the evolution of the case temperature when we applied current steps. So here we have nominal current. You see that the temperature of the MCPCB was slowly increasing until it reached a steady state value of around 36.5 degrees C. And when we had a diamond board, we could see that the steady state temperature value would be 29.3 degrees C. And this gives us a temperature difference of 7.2 degrees C, which then, and from here, we estimated the junction temperature, taking the values provided by the manufacturer, and we estimated sort of a 7 degrees difference in the junction temperature by replacing the MCPCB with diamond. And then we've done some measurements at 700 milliamps, and of course the difference is more prominent. So we had 13.2 degrees difference in the case temperature, which translated roughly into 13 degrees difference in the junction temperature. And of course, I can tell you right away that no, we will not use LEDs. We will not use these boards to mount LEDs, of course not. We want them to be low cost, unless we are using them in space, for instance. But if we are thinking of critical power components where temperature is really critical, then we could consider using diamond boards instead of MCPCB. And then we also evaluated the impact of the temperature on the lifetime, and depending on the aging process, again on the activation energy, the LEDs mounted on the diamond board will age 60 to 90% slower at 350 milliamps and 90 to 99% slower at 700 milliamps. However, to really take advantage of diamond, first we need to improve the metallization of the diamond boards, and we have to use adequate solder materials or thermal interface materials, whatever you want to call them, with high thermal conductivity. The conclusions of my talk. Okay, diamond has been successfully used to improve thermal management of different devices. And in the case of gallium nitride HEMTs, this can be done either by capping the HEMTs with diamond, by growing the diamond on the back of the gun wafers, or by bonding gallium nitride wafers and diamond substrates. We find commercially available power amplifier modules based on gallium diamond. And we also see companies such as Mitsubishi Electric or Fujitsu Limited involved in this research. We can also use diamond as a chip carrier, and we estimated that we would have a similar impact of polycrystalline diamond and single crystalline diamond carriers on the LED characteristics. We observed that these diamond carriers will improve the stability of the wavelength, and they will increase the LED lifetime significantly. And finally, if we use diamond as a power board, we increase the lifetime of the LED considerably when compared to standard metal core printed circuit boards. And now, of course, we can extrapolate results to other devices. And now I leave here a question. How can we use diamond for advanced packaging? And I come up with a recent proposal that was made by Stanford University, where they proposed to use diamond intertier heat spreaders and diamond thermal viases. So with the heat spreaders, we managed to homogenize the temperature of the hotspots, but then with diamond thermal vias, we can actually spread the heat from one tier down to the other until we reach the heat sink. And they estimate huge improvements in the efficiency and temperature in the case of high performance computing. And my funding agency, the FCT, and I'll thank you for your attention.
Great, Joanna. Before we move on to the second talk, I do have a question for you from T. Wei. He says, are there any solutions to do chemical mechanical polishing for the diamond, since I see the roughness of the diamond is high, which makes it difficult to integrate into packaging structure? Do you have comments on that?
Yes, I'm not an expert in mechanical polishing, but I can tell you that if you want to bond gallium nitride and diamond wafers, the roughness has to be below 1 nanometer. Typically, it should be in the order of nanometers. So you can actually, yes, if you start with single crystalline diamond, roughness is not so much of a problem. With polycrystalline diamond, it is, but you can decrease the roughness down to values of 1 to 2 nanometer with chemomechanical polishing. Okay, so yes, this is possible.
And then he asks, can we do the lithography etch method to pattern the diamond layer? This would bring more flexibility and opportunities for a diamond integration.
Yes, we can. Yes, we can. We can do it two ways. One thing I didn't mention, you remember I told you that when we grow diamond on a substrate, we must have carbon atoms there already. Otherwise, diamond will not grow. So there's a seeding procedure that has to be done. So if this seeding procedure is done selectively, we only grow diamond in particular areas where we have the carbon atoms. Alternatively, we can grow diamond everywhere, and then we can etch it with REE, with reactive ion etching, for instance, and oxygen plasma. So yes, we can etch diamond, and we can also grow it selectively.
Great, thank you, Joanna. Let's move on now. Jeroen van Duren is going to be talking in the second half of our presentation today. Jeroen, you can bring up your slides now. And then you can switch to laser pointer once you get up full screen. Okay, it looks good. I don't hear you yet, so unmute yourself.
Okay, you should be able to hear me now.
I can hear you now. Go right ahead.
Perfect. Well, first of all, thank you, IEEE Electronics Packaging Society, for the invitation. Thank you, Paul, for organizing it, and thank you, Joanna, for fantastic introduction into Diamond. That's really, really helpful. So let me make sure I have a window here that's blocking my view. I'm assuming.
We can see it fine, but go ahead and get that out of your area so you can see the full slide.
Okay, perfect. Yeah, I got it.
Okay.
Yeah, so I'll be talking about, I'll be introducing Diamond Foundry, and I'll be talking about single crystal diamond for thermally optimal electronics packaging. Now, we all know that diamond is the ultimate thermal conductor and electrical insulator. But what hasn't been the case, and that's different now, is that it's available in volume and cost efficiently. And I'll be talking about how we manufacture diamond, and I'll give you a few examples. As Joanna explained, diamond has a very high thermal conductivity. Our standard product is 2,200 watts per meter Kelvin. We even make 3,000 watts per meter Kelvin. And as you can see, that thermal conductivity at room temperature, is up to 20 times higher than that of silicon and like 7 times higher than that of copper. So that's very substantial. And for heat spreading, that has a huge impact. In addition, the single crystal diamond is a great electrical insulator. If you look at the thickness that's needed for a breakdown voltage of 10,000 volts, you compare it to, for instance, silicon and gallium arsenide, silicon carbide, and GaN, you can see that the diamond thickness is the smallest. And if you compare it, for instance, to like silicon, we're talking about a thickness that's 40 times smaller than that of silicon to get to a breakdown voltage of 10,000 volts. Yeah. So again, diamond has a lot of extreme properties. Here I'm only highlighting thermal conductivity and electrical insulation, but there are many, as Joanna has shown. Now, I'm happy to announce that it's finally happening. We made we've announced this a while back, the world's first single crystal diamond wafer. As you can see here, very nicely polished. Which is truly a milestone in the history of this technology, because this has been something that people had difficulties with in the past. Now, to get the cost down, you have to be able at scale. Production, you have to produce at scale. And we have been producing since early 2017. Our production volumes have increased dramatically since. Here on the left, you see a peak in one of our factories in Wenatchee here in the US, in Washington State, where you see a lot of our reactors, the CVD reactors that we use to grow our single crystal diamond. And on the right, you see a new factory that's being built in Spain, in West Spain, a few hours southwest of Madrid, in Trujillo. So as you can see, we're expanding pretty aggressively. Now, it's fantastic to be active in diamond because a lot of the diamond use is in power electronics and in compute and in RF, and it all has to do with energy efficiency and material use, like miniaturization. It's already fantastic to be doing that. But that's not all. We also want to be manufacturing, and that's what we have been doing, everything with zero emission. So, diamond is as green as it gets. First of all, we use all green energy, all renewable energy, like for instance in Wenatchee, Washington. Our factories are powered by the Columbia River. Yeah. And then on top of that, we crystallize greenhouse gas, methane, into diamond in our plasma reactors, which then are subsequently used, for instance, like power electronics to charge electric cars. Yeah. Right now, we are the largest buyer of high purity methane in the world, to give you a sense of scale. Now, how is diamond manufactured? That's 4 very important steps that we have developed in-house, 4 pillars. It starts with seeds. To be able to grow large diamonds, you have to have large seeds. And that's done by heteroepitaxy. So we have a capability to scale the diamond area as a result. So once you have these seeds, you grow ingots, diamond ingots. That's done by homoepitaxy. And our proprietary reactors, we grow over an area of 200 millimeter, which is very unique, with a plasma density 100 times higher than what's commercially available. So once you have these ingots, obviously these ingots need to be sliced. So we had to develop this ourselves, a high throughput singulator that's scalable with wafer size and provides low curve. So it's important with wafer singulation that it's high throughput and low curve and scalable. And then once these wafers are sliced, these wafers need to be polished, and we polish them up to an angstrom level smoothness. Quickly, a little bit on the growth. If you look in the middle, you see temperature versus pressure phase diagram for carbon, and what you can see is that the CVD synthesis conditions are low pressure and around 1,000 Celsius, which is actually where graphite is more stable than diamond. So the growth conditions are such that the diamond needs to be favored over the graphite. Hydrogen plays a big role in that, and your reactor design and the plasma conditions play a big role in that. And we're currently in our 10th generation of our reactors that have been developed over the past 10 years. And as I mentioned, 100 times denser plasma that is sustained continuously with novel electromagnetic resonance mode. Regarding smoothness, Joana touched on that. Diamond is the hardest material on the planet. So can you get it to atomic level smoothness? Yes, we can. We do this day in, day out. On the right, you see a 10 by 10 micron area as measured by AFM. You can see it's extremely smooth. You see in the middle a box plot for smoothness as measured with AFM, and you see it's just a few angstroms. And what's also important for various applications is flatness and total thickness variation. And as you can see, it's just a few microns. So very tight specifications as people are used to in the semiconductor industry. So our products available. So we cut our diamonds to customer sizes, to specific sizes. There's various rectangular sizes and surface finishes that are available. Our standard products are the DF200. The DF200 has a thickness of 200 micrometers, so 0.2 millimeters, with the roughness on the front and the back of 7 microns. That's an assay roughness of 7 microns, with a total thickness variation of less than 15 microns. And there we offer the thermal conductivity of 2,200 watts per meter Kelvin and 3,000 watts per meter Kelvin. We also have the DF200 ultra polished, same thickness, 200 microns, with a front side roughness less than 5 angstroms, so 0.5 nanometers. Backside 50 nanometers. TTV is tighter. It's 5 micrometers, and also there we offer both 2,200 watts per meter Kelvin and 3,000 watts per meter Kelvin. In addition, there's various forms of metallization available for various bonding techniques. And so, regarding the integration of diamond can be integrated using die attach and wafer bonding techniques. So the diamond can be metallized, or it can be used as a bare diamond. Then if you look at how it can be attached or integrated and how it can be bonded, the usual methods like soldering, sintering, thermocompression bonding, and as Joana touched on it, the surface activated bonding. And then how is this integrated? Well, thanks to the developments in 3D heterointegration. There's a lot of methods nowadays how to integrate dies and wafers together, or wafers and dies and dies. Yeah. So basically, you can do die-to-die bonding. You can do collective die to wafer bonding and wafer to wafer bonding. To explain a little bit on collective die to wafer bonding, shown here in the bottom from EVG. So what is done basically is the diamond dies are placed on a carrier, and subsequently this carrier that's populated goes into a wafer bonder together with the target wafer, and subsequently you permanently bond the diamond to the target wafer, and after that you remove this temporary carrier, and basically the diamonds have been transferred and permanently bonded to the target wafer. Yeah, so that's an example of collective die to wafer bonding. Metallization. Now, as Joana mentioned, diamond is chemically really inert. So to get good adhesion, you do need an adhesion layer. A very typical adhesion layer is titanium. Barrier layers depends on what you put on top for the metallization, but typical barrier layers are like platinum and nickel. Metallizations, this depends on the bond technology or assembly technique that you're using, but gold, silver, and copper are offered on the diamond. Yeah, and as with any metal stack, they can be patterned or they can be left uniform depending on the use. Yeah, so it's again, the diamond is very easily integrated, and to deal with the chemical inertness, it's putting down a proper adhesion layer on the diamond. Now, to give an example of bonding diamond to silicon without metallization, here you see TEM image of diamond bonded to silicon by surface activated bonding. Now, the fact that you have to use a TEM already tells you that there is barely a bond line thickness. You see a little bit of amorphization at the interface of a few nanometers. And that's obviously very important that you can get the diamond very close to the hotspot without a thermal interface material. Yeah, because the more effective the diamond is in its heat spreading. To give you a sense, these pull strengths are really high, like 80 megapascal. Thermal resistance is very, very low. It's like 1,000 times lower than a typical high-end TIM. It's for those thinking in TPR values. Measured values are like 10 square meter Kelvin per gigawatt. Or those thinking in different units, it's like 1 times 10 to the minus 4 square centimeter Kelvin per gigawatt. So it's extremely low. It's basically that's what to be expected when you get the diamond so close to the silicon. Now we're working on again on diamond with partners. As Joana showed, some nice work from BEA Systems where they got over 3 times the power density for GaN on diamond compared to GaN on silicon carbide, where obviously silicon carbide is already a pretty good substrate to use for RF, which is a substantial power increase, power density increase. However, we're working with partners to get it to 16 times higher than the state of the art, which is about integrating diamond with the latest improvements in both wafer technologies. As you can see here again, you have to zoom in. Yeah, this is a TEM image of the diamond bonded to the gallium nitride, and you can see again we're talking nanometers when it comes to the interface between the diamond and the GaN. Finally, to give you a sense of what we're doing in power electronics, what you see here on the right is the traction inverter from a Tesla Model 3, which is the state of the art. And on the left, you see our traction inverter that's based on diamond, taking advantage of the thermal conductivity and electrical insulation of the diamond. And where the power switches are silicon carbide. Now, thanks to the properties of diamond, you can now completely redesign the traction inverter so that you get a traction inverter that's 8 times smaller than the state-of-the-art traction inverter today in the Tesla Model 3. And you can see that the power density is 500 kilowatts per liter compared to 9 or the state-of-the-art traction inverter. And that's basically because diamond allows you to redesign the traction inverter. It allows you to basically go 3D, where people historically have always thought about designing these power electronic components in 2D. Yeah. That's a quick introduction to Diamond Foundry and some examples. Any more detailed questions, don't hesitate to send me an email at jeroen.df.com. And yeah, again, thank you all for attending. I'm open for questions.
Great. That's very exciting, both talks. First, a question for Joanna from Eric Young. He says he's wondering whether the improved performance of the LED experiment could also be achieved with a thin diamond spreader on an MC heat sink. That might allow an alternate approach to manufacturing. What do you think, Joanna?
Well, actually, we are currently doing some experiments where instead of having a metal core, an MCPCB, we are using aluminum nitride boards to mount the LEDs, and we are also coating these aluminum nitride boards with a thin layer of diamond, a few microns of diamond, because these will also have an impact. So replacing either the carrier or the board with a diamond plate is the extreme. You can start with silicon and you can coat it with diamond. You can start with, like I said, aluminum nitride and coat it with diamond. There are some reports in the literature where people have coated both heat sinks and even power boards with diamond, and they obtain significant improvements in the or decrease in the LED temperature. But I didn't have time to go through them all.
We'll look for that in a future talk. For both of you, Ninja Podar says, for the various gallium nitride on diamond approaches, what's the relative cost increase per wafer when you do think this way may be scale, and when do you think this will be scalable to 8-inch sizes with reasonable yield? So first of all, what's the cost per wafer increase? Joanna, do you want to answer first, and then?
Well, I
Phil?
don't have a number, but I can tell that, for instance, Akash Systems, they supply expensive RF modules. So a microwave amplifier, a power amplifier, is in itself expensive. So the relative cost increase when you bring diamond into the game is not significant when you take into account the benefits. For low cost or for lower cost components or applications, we cannot think of having a diamond board or a diamond plate, but we can think of integrating thin diamond films in specific places, whether, for instance, intertier, like the group in Stanford proposed, or coating carriers with diamond, or creating thermal vias from the top to the bottom of the carrier with diamond. I didn't mention, but diamond can also be electrically conductive. So we can even think of other, other possibilities to integrate diamond inside the packages.
And Jeroen, what about relative cost increase, and especially, is this expandable to 8-inch?
As you saw, Paul, our reactors are 200 millimeter diameter. So that answers part of your question. When it comes to cost, exactly as Joanna says, it's the system level cost that's important here. And that's where the diamond really shines in this case for in the RF space. When it comes, also the question was, when is this ready? Obviously, this is the GaN on diamond efforts. That's going to take multiple years. Yeah, it's not something that's going to be ready next year.
Got it. Jose, why don't you unmute? You have a question you'd like to ask.
Yes, my question is to both Joanna and Jeroen. As you know, cell phones use HBT transistors as their transmitter, and one of the limitations is removing the heat. And it turns out that because of that, designers have to design these power transistors to operate with only 2 slots as opposed to 4 slots, which forces them to be slow. So my question is it possible to use diamond as the collector in these HBTs as opposed to the standard gas material that is used. And as I said, this is a potentially huge market.
Joanna, do you want to take a crack at that?
Yes, I'm thinking about that. Well,
Okay.
you can grow diamond on gallium nitride, but you need to have a thin layer to protect the gallium nitride. Growing diamond on gallium arsenide directly may be very tricky because gallium arsenide would not be stable. And even if we were able to grow, that would mean having to decrease the deposition temperature, the quality would not be that high. But maybe with some engineering bonding some p-type diamond to as a collector, maybe something could be thought of, I would say, but I really have to give it a lot of thought. To
Jeroen,
give
have you looked at this application?
I have not, Jose, but Paul. So Jose, just shoot me an email. Let's talk about this offline, because it seems you're enthusiastic about it. So maybe this is something to look into.
Great. My thanks to both of our speakers this morning. I expect that within a week or so, we will have the video edited for this, and you'll be able to go back over in more detail and more slowly the information that our speakers have given you. Thank you, Jeroen, and thank you, Joanna, for joining us this morning.
Thank you.
Thank you, Paul.
Thanks, everybody. Bye-bye.
Bye.